Hello, am I audible? Can you please confirm? Please reply in the chat box if you are not in a position to. Okay, thank you. So let's wait for a couple of minutes. I will start after that.
Ma'am, yesterday I couldn't attend. So, is there anything like a recap video or something which can be shared?
I The videos are available. You can check those videos. Yesterday's session, I didn't take yesterday's session, so you can see my screen. You can see this problem solving session.
Yeah,
Yeah,
yeah.
you will find the links there. You can check
Okay, sure.
those.
Okay. Thank you.
I think we can start. People can join in between. So, good afternoon, everyone. Welcome to the live session for the course Sensor Technologies, Physics, Fabrication, and Circuits. This is week 5. Let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI, and I will be the TA for this session. If So, this session is mainly for problem solving, and I will also give brief summary of the topics those were covered in this week 5. If you have any doubt, you can unmute yourself or write in the chat box. I will be in the presentation mode most of the time, so I may not be able to check the chat box immediately, but I'll try to answer your questions. And if you have any doubt and I could not answer in the session itself, so I will cover those questions in the next sessions, or either in the next session, or we will have a doubt clearing session at the end before the exam. So let's start the session. So the first topic that was covered in this week was optical sensors. So optical sensors are used for detection of light, optical signal. Okay. Now there are different types of optical sensors. Those can be direct or indirect. Those were covered in the lecture videos. There are few examples of optical sensors. Those were covered. So first example that was discussed was photodiode. Okay. So photodiodes are used for detection of optical signal, and based on the material of the diode, the wavelength of light that it can detect, that can be varied. So what is a photodiode? It is nothing but a PN junction diode. You all are aware of PN junction diodes, but in case of photodiodes, the PN junction is used in reverse bias condition. Okay. So it is a PN junction used in reverse bias condition. Now why it is used as a is used in reverse bias condition? Because when PN junction is used in forward bias, that means when this is P, this is N, when P side is connected to positive and N side is connected to negative terminal of applied bias, and it is forward bias. In this configuration, the current in the diode will be already high. Therefore, the change in current due to photo generation or due to incident light, that will be negligible, that we may not be able to detect. It's not like electron hole pair or current will not be generated, or there will not be any change in current. It's not like that, but the change will be so insignificant compared to the total forward bias current that our measurement system may not be able to detect. So we will measure the change in a current using a multimeter or a SMU, source measuring unit. So our system may not be able to detect that change. Instead of if the PN junction is used in reverse bias condition, okay, when the diode is in reverse bias condition, the current through the diode is already less. Then when photo generated due to photo generation current changes, that change will be large compared to the reverse bias current, and that change can be detected by our measurement system. Now what happens? What is the working mechanism of a photodiode? Due to incident light, electron hole pair will be generated at the junction, and the junction will that photo generated carriers will contribute to the total current. Okay, so due to incident light, electron hole pair is generated, because electron and holes are generated in pairs. And that give rise to a change in the reverse bias current. Now the incident light can generate electron hole pair only when the energy of the incident light or energy of the incident photon is higher than the band gap of the material that is being used in the PN junction. Okay. So I'm trying to give you a brief summary. So I'm just writing down the points. That should be greater than band gap of the material. Now you know the relation between lambda and Eg. Lambda is equal to 1.24 by Eg, and lambda you can calculate this in micrometer, or if you take 1240 by Eg, this will be in nanometer. So suppose you want to detect visible light, the material that you are going to use, that will be different. And suppose you want to detect UV light, that material will be different. So the band gap of this material will be different. For example, lambda of UV will be less compared to lambda of visible light, right? Visible light is in the range 400 to 700 nanometer wavelength, and UV is below that. It has higher energy or higher frequency, less wavelength. So the material that you will be using, because lambda and Eg has inverse relation, so the material that you are going to use for UV detection should have higher band gap compared to the material that you can use for detection of visible light. Okay, so this detection is material specific. Okay. Now the current generated due to photogeneration or due to optical energy, that expression is electric current generated due to photocarriers the expression is I equal to eta q p naught by h nu. What are these terms? Eta is efficiency of our diode. Okay. Q is charge of electron, which is 1.6 into 10 to the power minus 19 coulomb. So I normally use the notation Q in the lecture notes, or in the books you will find E also, so don't get confused. P naught is the incident power of the photons. H is Planck's constant. What is the value of Planck's constant? 6.62 into 10 to the power minus 34 joule second. So you should remember these common constant values as well as their units. And U is frequency. So this is the first example of an optical sensor. The second example was a photoresistor. I'll just write down the term. So photoresistor is basically a simple device where the resistance of the material is changed due to incident light. Okay, and again to change the resistance or conductance, the frequency of the incident light should be sufficient enough so that it can generate electron hole pair. So again similar equation can be used in case of photoresistor also. Only the output signal is kind of different. In photodiode it is the electric current, reverse bias current, and in photoresistor we either measure resistivity or conductivity, both are same. Okay. I hope it is clear. Then the next topic was magnetic sensors. Now in this week mostly the physics related to these sensors were covered, not the sensor itself. So the concepts associated with magnetic sensors, those were discussed in this week in the lecture series. Was there was two concepts. First one was Biot-Savart law and second one was Hall effect. Okay, so the topics were, first one was Biot-Savart law. This law we have already studied in our class 2 level, so I will not go through it. Several examples were discussed in the lecture also. So what this law tells us, it gives us the magnetic field generated by a constant source. That constant current can be a current in an infinite wire or it is in a loop. It can be different, the expression is different, but it talks about the magnetic field generated by constant current source. Okay. So the magnetic field generated by, as per the Biot-Savart law, at position R is given by this formula. Mu naught by 4 pi. This is the integration over the path of the constant current source. Mu naught current into dl, that small length of the constant current source cross r dash, so by mod of r dash q. Okay. Now this is the general formula. This can be used to derive the expression for magnetic field generated by a constant current source. That can be a long wire or it can be a current carrying loop. Okay. Those few examples were already discussed. The second topic was Hall effect. So I hope most of the students here are from like ACE or AA background. So you have studied Hall effect. So Hall effect is mainly used either to detect the type of the semiconductor, whether the material is p-type or n-type, and the concentration of the majority carriers in a semiconducting material. So if it is a p-type material, then it is used to measure the concentration of holes, that is p, and if it is an n-type material, then using Hall effect, the concentration of electrons can be measured. Another parameter that can be measured using Hall effect is the mobility of electrons or holes. So what happens in Hall effect? Suppose this is a semiconductor block. Okay. My diagram is not that good, but I hope you will get the point. Suppose this is a block of semiconductor. It has a length L with W and thickness say D, and there is a current flowing through it. So let's consider this. This is X direction, this is Z direction, and this is Y. So this is the origin. There is a current flowing through the semiconductor, that is Ix, in this direction. So electrons and holes are moving in X direction, say, and magnetic field is applied, which is in the Z direction, positive Z direction, that is Bz. So suppose it is a p-type material, then the holes were moving in this direction before applying the magnetic field. Now when the magnetic field is applied, then using the right hand thumb rule, because holes and electrons are charged particles, and they will experience a force due to electric field as well as due to magnetic field. So because of the presence of magnetic field, the holes will move towards this side, and if the material is say n-type, then the electrons were moving in this direction because Ix is in this direction, so direction of flow of electrons is opposite. So this is for holes, this is for electrons, and again using the right hand thumb rule, the electrons will move in this direction due to the applied magnetic field. Now as you can see here, if it is a p-type material, there will be holes at this side of the material, and there will be concentration of holes will be less in this direction. Similarly, if it is an n-type material, then the concentration of electrons will be more in this direction, and concentration of electrons will be less in this direction. So due to this difference in concentrations, there will be an electric field. So holes will be in this direction, so this will be more positive here, more negative here. So this electric field direction will be like this. This electric field is known as so this effect is Hall effect. So this is the electric field generated due to Hall effect. So this is EH. And for in case of n-type material, the direction of electric field will be like this, because the electrons will move here, and so this will be more positive here, so the direction will be like this. So this is EH if it is an n-type material. So since there is an electric field in the Y direction, so there will be a voltage associated with this electric field. Voltage is equal to electric field is equal to V by L, right? V by L. So because of this electric field, there will be a voltage which is known as Hall voltage in this case. So Hall voltage will be E of H, and it will be this length. So this is W into W. So this is the Hall voltage. Now based on the magnetic field, this Hall voltage, it will be either 0, or based on the strength of the magnetic field, we will get some Hall voltage. Okay, so that is why this concept is also associated with magnetic sensor, because we can detect a magnetic field based on the Hall voltage. We can measure this voltage, and that can be correlated to the applied magnetic field. So, but in case of semiconductor, we use Hall effect to mainly measure the carrier concentration and mobility of the carriers. Okay. So I'll whatever I mentioned here, I will briefly note it down. Right. This concept is used to distinguish the type of material. Whether it is a p-type or n-type material. How it can be used to determine whether it is a p-type or n-type material, you can see the direction of the electric field for p-type material is in the positive y direction, and the direction of the electric field for n-type material is in the negative y direction if we use this coordinate system, z, y, x, y and z. Now like if we measure this voltage by considering the positive y direction, if it is a positive if the Hall voltage is positive, that means our electric field also positive, that means our material is p type. Again, if we measure the Hall voltage for a n type material and considering positive y direction, then the Hall voltage will be negative and electric field will also be negative, so it will be it is a n-type material. That's how we confirm, and it is also used to measure carrier concentration, and majority carrier mobility. This majority carrier mobility, if it is a p-type material, it can measure only Hall mobility, and if it is an n-type material, then it can measure electron mobility. Although there will be electrons present in p-type material, and in case of n-type material also holes will be present, but it can measure majority carrier concentration and majority carrier mobility. One important, like I will not go through the derivation, or I may be able, like I may need the derivation, so let me do that also. So let's consider this configuration, and under equilibrium the force in this system should be balanced. Now if it is a p-type material, the force experienced by holes will be in total it will be due to magnetic field plus electric field, so the total force will be Q into E, that is the force experienced by the charged particle due to electric field, plus Q into V cross B. This is the force experienced by a charged particle due to magnetic field, and under equilibrium it should be 0 to balance out, the forces will balance out each other. Okay, so let me write down the directions here. Here the current, this is in x direction, Why I am writing down the directions? Because that using the right hand thumb rule will be easier. You can work out yourself to find out the direction of the force on the electrons and holes. Okay. Now drift velocity of the carriers, that will be also in the x direction, because holes and electrons are moving in the x direction. Okay. Now magnetic field B, that is in z direction. And Hall voltage or electric field generated due to Hall effect, that is in y direction. Now I am considering EH or VH as positive if it is in positive y direction. Okay. So we already have this equation. So this will be E is equal to EH is equal to VH by W. Okay. Now you can equate this equation and then use different terms, and finally one term that is useful for us in Hall effect is the Hall coefficient, that we can measure in an experimental setup for Hall measurement. So what is Hall coefficient? That is what is useful for us. I will not go through the Hall derivation. RH, that is defined as VH D by I, this is Ix, into Vz, which is also equal to 1 by Ne or TEC. Okay. P is the whole concentration and Q is the charge. So VH we can measure using a multimeter. Okay. And D is this thickness. Ix is the applied current, that we already know, we are applying this current, and Bz is the magnetic field. So we can calculate this Hall coefficient value, which is equal to 1 by P into Q. So carrier concentration into charge. Now based on the sign of VH, we already know whether it is a p-type semiconductor or an n-type semiconductor. We know the value of Q. So these all the terms here are known, and we can calculate the carrier concentration from this expression from Hall coefficient. So Hall coefficient we can measure. Actually we calculate Hall coefficient in an experimental setup from VH. VH we measure and we calculate RH, and from RH we calculate P or N. Okay. P or N. That's how we calculate majority carrier concentration using Hall effect. So this was one topic that was covered. Is there any question? If there is no question, I will move to the next topic. So the third topic that was covered in this week was acoustic sensors. Now it is as the name suggests, these sensors are related to sound or sound energy or sound signal. either to detect sound signal or to detect something using sound energy. Okay. Now sound energies have different frequencies. So like you already know what is the electromagnetic spectrum. There are visible light, infrared, ultraviolet, all this. And in case of sound energy, we have three different like frequency range. First one is the infrasound. Those sound wave have frequencies below 20 hertz. Okay. And then the sound that we can hear, human being can hear, that is between 20 hertz to 20 kilohertz. Okay. And the third category is the ultrasound. Okay. Which is above 20 kilohertz. So you know that different animals and birds and insects use ultrasound to detect uh, like obstacles or detect some target using ultrasound. So what happens, uh, they generate ultrasonic sound and it will travel certain distance, uh, like hit the target or hit any obstacle, and it will come back to them, and based on the time it required. So this is how the nature actually we are inspired. Is there any question? Yes, Akshay, you can unmute if you have any question. No need to raise a hand, you can directly ask. There are not many people, you can directly ask. Okay, if you have any question, you can write in the chat box. I will check later. Okay, so similar to the nature, ultrasonic sound are also used for detection of objects, say object detection underwater, or that it was discussed in the lecture notes also that ultrasonic sounds can be used, or sound energy in general can be used for detection of objects in various situations where optical energy or optical signal cannot be used, say in a smoky environment, if in an like maybe in an industrial setup where it is the precision of the detection is necessary, but we cannot use a visible light or any other electromagnetic signal or optical signal. In that case, sound energy or acoustic sensors can be used for detection of objects. Okay. Now, so what are the advantages of these sensors? As I mentioned, can detect environment with low visibility. You can check the underwater object detection. I think acoustic sensors are used. I'm not sure, but you can check. Another advantage is that it can detect transparent objects. visible light cannot be used to detect transparent objects because it will not reflect back, or the transmission will not change. So ideally the transmission through a transparent object for visible light will be 100% one. So visible light cannot be used for detection of transparent object, whereas optical acoustic sensors can be used. Now the different sensing mechanism those are used in acoustic sensors are typically either resistive type or capacitive type. So in both of these type of sensors, there will be a diaphragm that will bend or deflect based on the sound energy or the frequency of the sound energy, and there will be another electrode, back electrode, this is the diaphragm. So and sound will travel to this diaphragm. And there will be a spacer layer in between. Now this is our first electrode and this is the second electrode. Now the resistance of this whole setup may be different based on the deflection of this diaphragm. So when this diaphragm deflects, the shortest distance for the electrons to travel will be like this, okay, and that will vary based on the deflection. So the overall resistance of this setup will also change. Now if we are using it as a capacitive arrangement, capacitive configuration, now due to the deflection, the capacitance between these two electrodes will be different. So based on that change in capacitance also, the energy of the optical signal or the intensity of the not optical signal, the acoustic signal can be like it can be correlated, so that we can quantify the value, quantify the acoustic signal, its frequency, or suppose we are using it for detection of some object, then we can determine the distance based on the change in resistance or change in capacitance, and we can correlate it with the distance between the sensor and the targeted object. Okay. So this is the third topic, and the last topic that was discussed in this week was microfluidic sensors. So microfluidic sensors have become popular mainly for biomedical purposes or in medical purposes, because these are, so what happens in biological sensors or biomedical sensors is that most of the time the sample that you will get, that will be very less. Suppose so you cannot have like a large volume of blood sample or saliva sample, so you want your sensor to be it should be precise. Obviously it should detect what you it should detect the targeted material, targeted analyte. Also it should use like very small amount of sample. Say you are using a blood sample, so microfluidic sensors, these are already very small. There are small micro channels, so the characteristics length is in micrometer. So these sensors are very small, so the sample that is required for detection is also very small. That is why these sensors are more popular or mostly used in case of biomedical sensing. Also these sensors can like we can make different configuration or different types of microfluidic sensors due to the advancement of fabrication techniques, so that also plays role. We know that the resistive sensors or capacitive arrangement, those are very simple sensors, but with the advancement of like fabrication technology, we can make very small devices, very small sensors on a chip, and that will require very low power, and the cost is also less, because so those can be made using standard fabrication technique, and you can produce many sensors at once, and you can make disposable sensors also, because the overall cost is very less. You can optimize the fabrication process and the material or the substrate that you are using, so overall the cost is also less. You can make, that is why you can make those disposable also. And in biomedical sensing, in most cases you want disposable sensors, so these are mainly used for biomedical sensors. It's not like these cannot be used for other sensors, but mostly these are this has certain advantages, as I mentioned, in case of biomedical or biological sensing. Okay. So what are the applications of microfluidic sensors? First application, I am taking this from lecture note, you can refer to that. Lab on chip. So what is lab on a chip? It's like you have a small sensor. Okay. You can put your sample here, say blood or saliva sample, I don't know, and you can like do a test. You know those glucose sensor, like small devices. You don't have to go to a like laboratory or a hospital to detect something. So these that became possible due to the fabrication of smaller samples, like smaller sensors. So suppose we want to detect a target, some material, some biological material, presence of which will give us the indication of a certain disease. So we can make those specific sensors for detection of specific target using a microfluidic sensor configuration very easily, and those are known as lab on a chip. You don't have to go to the hospital to get it checked by a trained professional. You can do it yourself, and you can get the results much quickly. So normally what we do, we go to the hospital, we do the test, and the report they give after 1 or 2 days, in some cases maybe much more than 1 or 2 days. So using these sensors, those tests can be done much easily at a much lower cost, and without going to a hospital. You can do it at your home also. Next application is organ on a chip. If you remember, I hope that you have watched the videos, organ on a chip. So these are to mimic like different organs, say a part of our lungs, a part of our liver, so that scientific experiments can be done. Suppose these are mainly used for drug testing. Suppose someone is designing or someone is synthesizing a new drug for certain disease that will be for targeted some liver disease, then instead of applying those drugs to actual human beings, using a microfluidic sensing technology, we can make a like device that can mimic the function of a liver or function of a lungs of a human being, and the drugs can be tested on those like fabricated devices instead of human being. Okay. and these are used in biosensors or biomedical sensors. Can be used for chemical sensing also. Okay. Now these microfluidic sensors are typically made on two types of substrates, either glass or PDMS. Other substrates can be used also. Many sensors are made on silicon substrate, because using so if we use silicon substrate, we can use the standard fabrication processes associated with silicon very easily. But glass and PDMS are those are low cost option, as well as those are transparent also, may be useful in certain cases. So those are typically used substrates in case of microfluidic sensors. PDMS is flexible, so that is one advantage of this. And what else was discussed? Different types of microchannels were discussed. There are different types based on the shape of the microchannel. And fabrication techniques, briefly it was discussed also. The fabrication techniques can be either lithography. Lithography is selective patterning and selective removal of material from a substrate. So lithography can be of two types also, either photolithography, where a UV light source is used, or E-beam lithography, where a beam of electron is used for patterning. There are other techniques of like fabrication also, like some soft lithography, and I think replica molding, that was the technique that was discussed in the lecture videos. So there in this course, one part is fabrication of sensors. Those will be discussed in the upcoming week. So I will discuss more about the fabrication of different sensors in those weeks. Okay. I hope this like summary of week 5 is clear, and if there is no question, I will move to the next part of the session. I will discuss some of the problems. So there is no question. Let's go to the questions. Why do we need indirect sensing rather than direct sensing in case of detection by optical sensors? First option is for more accurate quantification of output signal Second option is to have an increased resolution of detection. Option 3 is for easier implementation. And option 3 is for non-context sensing. So which of these options are correct? Please give me the answer in the chat box. No answer? Okay. What is indirect optical sensing? Indirect sensing means when we need another component to detect optical signal. Okay. Either to detect or to analyze. Right. Often this when we need another not signal, this component. The component is often electronic. Okay. Electronic system, right? So say suppose you have a substrate here. This is substrate. This is your sensing element or sensing material. And you are detecting some target material or target analyte. Due to the reaction between the sensing material and the target material, the color of this material at the top will change. Now you can detect a change in color directly from your eyes also. But suppose you are using indirect sensing, you are not directly detecting it by using your eye. You are taking the image of this color. Okay. We are taking the image of this top part of the sensing element, and you know when you take the image, so in computer you will get RGB values, right? Say this sensing material after the reaction with the target analyte will give you a color red. So if it is like pure red, then the RGB value that you will get in your computer, that will be 255,000. So this is the R component, this is the green component, and this is the blue component, right? Green and blue component is 0 and R component is 255, that is highest. Okay. Now there is two types of detection: qualitative detection and quantitative detection. What it means is that suppose you want to know whether the target material is present or not. It is a yes no question. Then it is a quantitative detection. It is like binary, either 0 or 1, yes or no, right? I should have written its opposite way. So this is known as qualitative detection. Qualitative detection of target material. Now what will be quantitative detection? You want to know whether the target material is present or not. Also you want to know what is the concentration of the target material. Okay. Now see how you will get the concentration of target material. This R value, that if the target material is present, that will be R value will be non-zero for the RGB component, the R component. But this R value can be in between 0 to 255. Typically in our computer, the RGB value, those will give you a 8-bit number. Okay, it's of 8-bit, that is why it is 0 to 255. It can take value between 0 to 255. Okay, so that means 0 is for no target material, say, and from 1 to 255, that will give you indication of different concentration of the target material. Say higher the concentration, higher will be this number. Now you can calibrate your sensor first by using known concentration to the RGB value, so that you are now sure that you get this calibration curve. So this is your concentration and this is your R value, right, for this RGB component, and that will give you some like a graph. You can you get this calibration curve Now you can do a qualitative detection using this kind of sensing arrangement. Instead of this indirect sensing, if you use a direct sensing, say you are just by looking at the color of the top part of the sensing element, you are determining whether the target material is present or not. That will give you a qualitative detection of the target material, not quantitative. You cannot quantify the concentration easily just by looking through a tag. So the first point here is for more accurate quantification of output signal. So this is correct. Using indirect sensing, using an electronic system or using some circuitry, we can interpret our optical signal better. And the second point is to have an increased resolution of detection. So here I have mentioned that the RGB value can be between 0 to 255. So that means what? So the color of the sensing element, this is red color, say. So the RGB values can be some R 0 0, it can be R dash 0 0. The smallest difference between R and R dash, that is the resolution of your system. Now if it is a digital imaging kind of system, that will give R and R dash value between 0 to 255. That means 256 is 2 to the power 8. So this is a 8-bit system. The smallest value of R and the smallest difference between R and R dash, that will be 0 0 0 1. So there will be 7 zeros and 1. So this is the resolution of your system. Now instead of an 8-bit system, if you can design a 10-bit system, say 12-bit system, then your resolution will be better. This smallest difference between R and R dash will be smaller in a 12-bit system compared to an 8-bit system. So indirect sensing can actually improve the resolution of a detection. In case of direct sensing, it is either 0 or 1. So the difference is 0 and 1. Like you only get 2 states, but here you can get 2 to the power 8 states. That means your overall resolution is increased. So this is one advantage of using indirect sensing. So this is also true. This is true. Now this point is for easier implementation of sensor. As you can see, this is not an easier implementation. Indirect sensing is not easier. Direct sensing is obviously easier. You don't need to design an electronic system. You don't have to do this calibration curve between this R values and concentration. So it is not an easier implementation, but it can give you precise measurements. So this is false. Okay. For non-contact sensing, in general, optical sensing is a non-contact sensing, so this point is not particularly true for this context of this question. Okay, so I hope it is clear. If there is no question, I will move to the next question. Question 2 is, which of the following is true for photodiode? First option is the wavelength of light must be greater than the cutoff wavelength. Second option is there is no photo generated current in forward bias. Option C is the photodiode is used in reverse bias in general. Option D is the reverse bias current is sufficiently larger than photo generated current. Which of these statements are true for photodiode? You can tell me the answer in the chat box. No answer. Let's go through these points one by one. So first point is there any answer? Let's see. Yes, option C is correct. What about others? Others are true or not? Option C is correct. Photodiode is used in reverse bias in general, so that we can actually get a change in current due to photogeneration. So the first point is the wavelength of light must be greater than the cutoff wavelength. So if this is the material, this is some material and light is incident here, the energy is h nu. Let's consider this light can remove electrons from this material, so h nu will be equal to phi plus km. So what is phi? The work function of the material or the energy required to remove an electron from the material, and km is the kinetic energy of the removed electron. So if electron is say ejected from here, it is removed, then km is the kinetic energy of these electrons. So phi is the work function or energy required to remove an electron. Okay. For semiconductor, this phi is this energy will be equal to Eg. Okay, it is not easy. To work function is different compared to easy. So I'm sorry. So this energy will be equal to h nu c. So this is the cutoff frequency, or the frequency, that minimum frequency that is required, so that if a photon has a frequency of if a photon have a frequency of nu c, then only it can remove an electron from the surface. So h u c we can write it as h c by lambda c. So this is the cutoff wavelength, right? So in this expression also we can write hc by lambda is equal to hc by lambda c plus km. Now here lambda is the wavelength of incident photon, and lambda c is the critical wavelength or cutoff wavelength. Now an electron will be ejected only when, so this term should be greater than this term, so electrons will be ejected, so that means km is greater than or equal to 0. This will be only when hc by lambda is greater than hc by lambda c. That means lambda should be less than or equal to lambda c. So the wavelength of light must be less than the cutoff wavelength, right? Or the frequency should be more than the cutoff frequency. So this first statement is false. The second statement is there is no photogenerated current in forward bias. So as I mentioned earlier also, in case of forward bias also, photo generation will happen. Like if the energy of the incident photon is sufficient, then it will generate electron hole pair in case of semiconductor. But it's just that the forward bias current is already very high, so we may not be able to detect the photogeneration current, the current due to photogenerated carriers. Okay. So the point here is that forward bias current is much higher typically in hundreds of microampere compared to photo generated current. So this is typically in the range of tens of microampere, right? And therefore may not be detectable by our measurement system. I don't know why I'm writing this. Okay. So the second statement is false. It's not like there is no photo generated current, but it is not detectable actually. Third point is already true, that we already discussed. And the last point is the reverse bias current is sufficiently larger than the photo generated current. No, it is less, and that's why we can detect the photo generated current, right? So this is also false. So our answer is C. Let me write down the first question. It is a third question. It is a numerical question. You can try to solve it along with me. A photodiode. You have similar questions in the assignment. In reverse bias condition, with an efficiency of 50% has a current (50 nanoampere) due to optical signal detection. What is the minimum power of incident light with 100 terahertz frequency? So this is the question. I will solve the question. I am expecting that you will also solve this along with me. You have similar questions in your assignment. First, let me write down the terms, the values, parameters, those were given to us. first it is in the reverse bias condition, right? Second is efficiency is given 50%. Eta. Efficiency in case of photodiode we denote using eta. So what expression that we are going to use I have already discussed. So we are going to use these expression. Okay, I am using similar notations here. Efficiency eta is equal to 50%. That means it is 0.5. Current I is given as 50 nanoampere. Another thing that is given, frequency 100 terahertz, frequency of incident light. Hundred terahertz means 10 to the power 12 hertz. We have to determine the minimum power of the incident light. So let's consider minimum power of incident light as P naught. Okay. Now I will use the expression of current in photodiode, right? So current I is equal to, what is the expression? Eta Q P naught by H nu. Q is the charge of electron, right? Which is equal to 1.6 into 10 to the power minus 19 coulomb. And H is Planck's constant, which is equal to 6.626 into 10 to the power minus 34 joule second. Another Planck's constant value that you will get in electron volt second also, but for this calculation we are going to use Planck's constant in joule second unit. Okay. So I is given, which is 50 nanoampere. You can put the other values. Eta is 0.5, Q is 1.6 into 10 to the power minus 19. P naught we have to calculate. H is 6.626 into 10 to the power minus 34, and nu is 100 terahertz. Writing everything in standard unit. So the P naught incident power that we will get, what will be the unit of incident power? So what is the unit of power? That is in watt, right? So P naught we will get in as in with the unit of watt. You can do this calculation. Tell me the answer. What is the answer? There is no answer. I am writing the value here. You can check if I have made any calculation mistake. So this is equal to 41.4 nanowatt. I'll go to the next question. What is the sheet resistance of an N-type photosensitive film if the thickness of the film is 50 micrometer, electron mobility is 250 centimeter square per volt second, when photo generated carriers per second is 10 to the power 14 per centimeter cube per second. So this is the question: what is the sheet resistance of a photosensitive film of thickness 50 micrometer? Electron mobility is given 250 centimeter square volt second, and photo generated carriers per second is 10 to the power 14 centimeter cube per second. And another information is half-life of electron is 0.8 second. Try to solve it. I am giving you a few minutes. The necessary equations are there in the lecture notes. Let me solve this. Okay. So the expression that we are going to use, the conductance of a semiconductor so this is basically the change in conductance due to photogeneration, you can say. This is sigma is equal to zq mu n tau n plus mu p tau p. So here mu n is electron mobility, the unit is generally expressed as centimeter square per volt second instead of meter. Mu p is hole mobility. Typically in semiconductors, electron mobility is higher. Okay, similar unit. Tau n is like lifetime of electrons. This is the unit is in second. Why tau n is important in case of conductance in a semiconductor in case of photogeneration? Because after the point tau n, the electron hole pair will be recombined and it will not contribute to conductance or flow of current. So it will contribute to the conductance value as long as it is like electron is in conduction band and holes is in valence band. Once it recombines, then it will not contribute. That is why this tau n and tau p term is also coming in this expression. Tau p is lifetime of holes. This is also in second. Q is charge of electron and Z is number of photogenerated carriers per second per unit volume. So this is the expression. Okay, now we are going to use this. Now in case of for if mu n tau n is very greater than mu p tau p, which is true in case of most semiconductors, we can ignore this part here and we can write sigma is equal to Z will be n because that is so here this is the number of photogenerated carriers per second per unit volume. This is number of electrons as well as number of holes. Now these electrons and holes are generated in pair. So if we denote the number of photogenerated electrons by n and if we denote the number of photogenerated holes are by p, then n will be equal to p, which will be equal to z. Okay, so let me write here as n q mu n tau n. Now we know all these values. We have to calculate conductance. N is given as photogenerated carrier per second is given as 10 to the power 14, right? So this is 10 to the power 14 into 1.6 into 10 to the power minus 19. Mu n is given as 250. Everything is in centimeters, so I am not worrying about the unit. if one unit is given in meter, another unit is given in centimeter, then you have to do the required conversion. 250 into tau n is 0.8. Okay. So this will be equal to, what will be this? 10 to the power 14 into 1.6 into 10 to the power minus 19 into 250 into 0.8. So this is 3.2 into 10 to the power minus 3. What is the unit of conductance? It is ohm inverse centimeter inverse, right? Siemens per meter, that is the unit of conductance. So we can write is as ohm inverse per meter inverse, because everything is in centimeter, so the unit is ohm inverse per and centimeter inverse. Okay. Now what is seat resistance? We have to calculate the seat resistance of the film. Seat resistance is the expression for seat resistance. It is denoted by RSH is equal to rho by T. Okay, what is rho? Rho is the resistivity, and T is the thickness of the film. So now you can see that the thickness information is given, the thickness of the film, length and width is not given, and we have already calculated conductance, so we can determine the seat resistance. Another expression is, so you know resistance is equal to, R is equal to rho L by A, which is rho L T into W, length and width. Okay, so rho by T is equal to R into W by L. So another expression of seat resistance is R into W by L. So if in your question these values are given, then also, like, instead of, so from if the R value you can calculate and W and L is given, then you can calculate also seat resistance, and if the thickness is given, rho you can calculate, then also you can calculate seat resistance value. So rho is equal is resistivity. Rho is inverse of conductance. Resistivity is inverse of conductance. So this is equal to 1 by sigma into 1 by T. Right? Now you have all these values. You can put 3.2 into 10 to the power minus 3 into thickness is given as 50 micrometer. So 50, this is in unit ohm inverse centimeter inverse. So 50 micrometer also I am writing is in is in minus 4, 10 to the minus 4. So what will be this value? 3.2 into 10 to the power minus 3 into 50 into 10 to the power minus 4. This is 1 by this. The unit of seat resistance is denoted as ohm per square. Okay, this is the unit of seat resistance. So the value is 6.25 into 10 to the power 4 ohm per square. I hope this calculation is clear. If you have any doubt, you can ask. I'll go to the next question. So this question is on Hall effect. This is a block of material. This is L. This dimension is L. This is W. This is D. Current is in X direction. So this is Z. This is Y. This is X. There is a magnetic field BZ. Okay. And it is a so there is an electric field in Y direction EH. Okay. So we in the question given L is equal to 10 to the power minus 1 centimeter, W is equal to 10 to the power minus 2 centimeter, and D is equal to 10 to the power minus 3 centimeter. Current Ix is equal to 1 milliampere. Bz applied magnetic field is equal to 5 into 10 to the power 2 Tesla. This is the unit of magnetic field. And Hall voltage is equal to minus 6.25 millivolt. So this is Hall voltage. Okay. So the question is calculate majority carrier concentration. Let me solve this. You can solve along with me. Let's consider it is a p-type material first. Okay. If it is a p-type material, for this configuration, total force should be 0, right? So that everything is balanced out. So F is equal to, as I mentioned earlier, force on the charged particles will be force due to electric field plus force due to magnetic field, that will be equal to 0. That means Q into EY, electric field is in Y direction, is equal to Q into Vx Bz. So these two forces will cancel each other. Vx means velocity of the carriers, which is in the x direction. So the electrons or holes are moving in the s direction because current is in x direction and magnetic field is in z direction. Now this is our first equation, and induced voltage is the Hall voltage. hall voltage is, for this configuration, this is EH into W. So this is electric field due to Hall effect. This is our equation 2. So this is equal to Vx. Using equation 1 and 2, you can get Vx, Vz, W from 1. Right? I hope it is clear. Next, drift velocity expression is, which is Vx is equal to current density is Jx by Q into P. So Jx is current density, which is equal to Ix by total area, which is equal to Ix by W into D. This area, this cross-sectional area, which is W into D. So this is Ix by Q into P into WD, right? And Hall voltage again will be VH. From this expression, we'll put the Vx expression. So this will be Ix Vz by QP D. So this is the Hall voltage. Okay. So P is equal to Ix Pz by QD VH. Okay. In case of P type, for N type, so this is for P type. For N type material, this will be minus Ix, the sign will be opposite, Vz by Qd into Vh. Now here you can see our Vh, Hall voltage, is negative. As I mentioned earlier, if our coordinate system is like this, then the electric field due to holes will be positive and magnetic field due to electric field due to electrons will be negative. That means if the Hall voltage is negative, that means our material is of N type. Right? So we will use this expression. Minus Ix is given as 1 milliampere, so that is 10 to the power minus 3. Bz is given as 5 into 10 to the power 2 Tesla divided by Q is 1.6 into 10 to the power minus 19 into D is 10 to the power minus 3 centimeter. I am writing everything is in meter, see, because every other parameters are in standard unit. So 10 to the power minus 3 centimeter is 10 to the power minus 5 meter. Okay. Into VH is negative, minus 6.25 millivolt. So you can see overall N we will get as positive and the value will be 10 to the power minus 3 into 5 into 10 to the power 2 divided by 1.6 into 10 to the power minus 19 into 10 to the power minus 5 into 6.25 into 10 to the power minus 3. Okay, so this is minus 2 Tesla. So this is 5 into 10 to the power 21 per meter cube. So in centimeter cube, because that is the unit that is normally used, it will be 15, 15 per centimeter cube. Okay. Then this is how we can calculate carrier concentration. In questions, it may be given as the Hall coefficient RH, which is Hall coefficient. I think in one of your assignment question, Hall coefficient value is given. So RH is equal to basically electric field due to Hall effect divided by current density into magnetic field. So that is EH by J into B. So this is the expression, and when you if you solve this, if you put this values, you will get this as VH into W by B into I, which is equal to 1 by N into Q. Okay, so if Hall coefficient is also given, then also you can calculate the carrier concentration value. And if not, if the Hall voltage is given and the other dimensions are given, the procedure to calculate the carrier concentration is this, by using this expression. And from where we get this expression, I have given you the derivation here from the force balance equation, and then you can substitute other values, other expressions, and get the final expression for carrier concentration. I hope this is clear. You can ask me any question if you have any doubt. So we have few more minutes. If you have any doubt, you can ask. I will share these notes, and if you have any doubt, you can ask in the next session also, or if anything is not clear. So I have stopped sharing. If there is no doubt, then let's stop the session here. Thank you for attending the session. I hope it was useful. Let's meet in the next session.